8.2, slope fields and Euler's method. So what we're talking about when it comes to what is a slope field is a picture. It's a field of smallly drawn pieces of slopes at points on a coordinate grid. And to the general, it's defined a solution to the general differential equation in the ty plane. Remember when we were doing 8.1 in differential equations, basic ideas, we're always going to be dealing in that. Instead of xy, we're going to do ty plane. So a slope field gives us a little bit picture of what the solution could be. So we want to try to sketch. The biggest thing about finding slope fields is we want to bring in a procedure of sketching a slope field by hand, where the differential equation, and this a lot of times the book will give us y prime for the differential equation notation, but we're going to go ahead and just take a small number of points. We're going to be able to plug into the differential equation and find the actual slopes. Remember, derivative is slope. And then usually it says here a 4x4, 5x5 grid of points suffices, but it could be smaller. It could even tell you just what quadrant, maybe only one quadrant they want. At each selected point, we find what actual little line segment of slope is, and then we draw a little approximation. So quick sketch. If I have this point 1, 1, and I plug it into some different equation, and we say, oh, the slope is 1, then we draw a line that looks like this. That would be the y equals x line. That would be kind of that slope. But what if it was a slope of 3? So we make it a little bit steeper. But what if it was a slope of 10? We make it a little bit steeper. But notice how we cannot tell exactly what that value is from this little piece of drawn slope. And it's just a tiny segment. So we don't know maybe the difference between a slope of 8 and the slope of 20. And the thing is, what if we get undefined? So we may even have to draw undefined as a vertical slope. Well, those are easy. And also, we should be able to tell if it's a horizontal or zero slope. So we can have this where we want to go ahead, maybe the key thing to look for are where our slopes are going to be 0, our slopes are going to be undefined, and we want to know where our slopes are going to be positive, and we want to know where our slopes are going to be negative. And then if we can at least draw positive, negative, 0, undefined, we can get an approximate idea of what the solution to the differential equation would look like. Remember, the solution to a differential equation is always a function. So we're going to go ahead and we're going to try to do a couple by hand. So I'm going to go ahead and start with number 5. We're given y prime is equal to negative 2y. So the basic thing is we want to go ahead, and this problem in the book gives us a chart to start with. And they said, okay, we're not going to do a full coordinate grid, but maybe we could go ahead and we'll do it for when t equals 0, t equals 1, and t equals 2. So in order to fill this out, I need these numbers. So I'm going to go ahead and have these 9 points that I want to grid, and that's how I'm going to draw my coordinate. So I'm going to go ahead and I'm just going to say, well, I got 0, 1, and 2. And then for t, and then for y, we have 0, 1, and 2. So I'm going to have these 9 points. So in order to find how the slopes go for each of these points, I'm going to plug in my t and my y. But if you notice in my differential equation, there is no t. If that's the case, I'm only plugging in y. So it does not matter when I plug in y going across. These are going to be constantly going across in that direction because of not having that t function or variable, t variable in our differential equation. If I plug in y equals 1, if I plug in y equals 2, so that's where I can do it this way, and this was easy. They told me where I wanted to just graph, and it was easy to just plug in and evaluate. So then if I go ahead and evaluate it at this, I have horizontal lines here for my slopes. I have a -2, which may look like this when y is 1, and I may have a -4, which is slightly steeper when y is 2. So this is it. This is all they want us to do, was to graph this slope field with these given points. So if we did another one, and if they give us initial value, like number 9, sometimes they'll give you a differential equation and a point that pins down the general field or the general solution to the differential equation, and they pinpoint it. They pin it down. They want a particular solution going through this point. So in this one, they want the same chart, but they have it, they want you to draw this function that's a possible solution here for this particular point. So we'll have t equals 1, 2, I'm sorry, start that over. T equals 0, t equals 1, t equals 2. And then if we're going to be plugging in t into this equation, notice then we have a constant going down our columns because we have no y variable in the differential equation. Plugging in 1, and then if I plug in 2, and actually this, I've missed one, he has t equals 3. So let's go ahead and plug that in, and then I would have 2's going down my column. All right, so then now they said, okay, do a quick sketch of the slope field and then draw a particular solution through this point. So let's try drawing this one. Noticing we have 0, 1, 2, 3, but y 0, 1, and 2. So I'm only going through these points. And then I've already made my slopes, so I can go ahead and try to graph them. When t equals 0, I have -4 slopes. When t equals 1, I have -2 slopes. And when t equals 2, I have 0 slopes. And when t equals 3, I have 2 positive. So I notice I'm looking for the positive, the negative, the 0, the undefined. And then it says go through the particular point of 2, 1, which is this one. And I'm going to try to follow from here. If I was to follow this, I would see that I would kind of get this parabola this way maybe. So this is the way it would, my solution would look. Remember, if you need to think about it, if I took the antiderivative of this function, differential equation, I would get a t squared, which I know is a parabola, so I know I'm on the right path for that. But all these differential equations won't be that easy to, be able to check our work with. So let's do one more that is such a case. Number 13, our differential equation is this, given this point to pin down and this point. So there's a reason why they give us 2 initial points to pin down. And notice this is another way of saying a point, 0, -2, and -2, 0. So we would do, if we wanted to draw a slope field real quick, we can. But the key thing is we're looking for where we would be undefined. We may have to make a chart. And I know then in this case, they did not give me a chart to restrict with. So I'm going to go ahead and do some kind of basic window. If we want to do, in this case, maybe a 4x4. and then we could see from there. But the long story short, if I go to draw all these little slopes, and then I want to pin down at the point 0, -2, and at the point -2, 0. So this one, I'm going to draw the actual possible particular solutions by saying it roughly looks like this. And the reason is because we have a point where we're kind of undefined. So when we're in y equals -1, we would be undefined in our, so I'm looking for undefined places in this one because of having the rational expression. So remember, you can draw a bunch of slopes. I was trying to save time from drawing a ton of little slopes here. For number 26, they give us this differential equation, and for part A, they say, okay, what is the solutions that are constant for t greater than or equal to 0? So I knew I only wanted to do the first and fourth quadrants. And then they're saying, or the equilibrium solutions. Basically, what I want to know is, where are the slopes 0? And what I know, if this is the slope function, I would set it equal to 0 and go ahead and solve for where it would be 0. So we know that this would have been a quadratic trinomial. It's already factored. Zero product property says set each factor to 0. We know then that I'm sorry, strike that, y is going to be -1 and 2, we would have 0 slopes. And then what we want to do is then graph this and try to find where we have increasing slopes and where we have decreasing slopes. So if we went ahead and I'd done the slope field, I went from 0 to 4 on the t-axis, and on the y, I went from -3 to 3. So I want to go ahead then. I have all my slopes in, and I want to know when I'm increasing slopes, or this function is increasing, differential equation, when y's are greater than 2 and when y's are less than -1. I can see that I have positive slopes. And then I can say, well, I'm decreasing for this differential equation when my y values are between the -1 and 2. Remember, -1 and 2 are where I have slopes of 0. So these are where I'm going to be increasing and decreasing between. So notice they were y values. My differential equation had y's. Then it says for part C, it says which initial condition y of 0 equals a lead to solutions that are increasing in time and decreasing. So that's what we wanted to say is, well, wait a minute. If y is greater than a, then let me write it out this way. We want to know if it was something else than what we were already given. So here we would say y is greater than a, y is less than the -1, and then we would be between that a, would have to be in between the -1 and 2 where we were constant. All right, so then D says sketch the slope field and verify its consistence with the parts we've already done, and that's what we did already. All right, this is the end of 8.2 part 1. The second part of the 8.2 will be about Euler's method.